Thank you very much for the introduction, and thank you all for joining my talk on a concurrent program logic with a future and a history, which is joint work with Roland Meyer and Thomas Wies. So we are interested in program verification, and this quote from the late 70s suggests that we can focus. Okay, I briefly switch to the mic. Is that better? Okay, cool. So, and this quote from the late 70s tells us that we can focus our efforts on algorithms and data structures separately. And in this work, we are focusing on the latter part, on the verification of data structures using separation logic. And we are using separation logic because it has been proven an invaluable asset to deal with the resources that data structures manage. And we have a twist to that, and that is automation. So we are interested in generating these proofs for data structures fully automatically. And to do this, we need to overcome several challenges. Two challenges. So the first challenge is that we need to handle complex unbounded updates, and the second one is linearizability. If you're not familiar with linearizability, it's not a problem for this talk. I will give you a kind of a brief overview of that in terms of temporal reasoning later. But let's start with the complex and potentially unbounded updates first. So, and I'd like to tell you what I mean with that. To do that, let's consider this sorted list example. So the sorted set example. So this set is organized as a singly linked list of nodes. These nodes have all keys. And there are some sentinel nodes here. This is the minus infinity and the infinity. And there are also some marked nodes. This is the red X. And it's really common practice in concurrent data structures to perform deletion in two steps, to first mark a node and say, you know, this is now deleted. It's no longer considered to be part of the set, and later on unlink that. We speak of this marking step as a logical deletion, and then the unlinking would be a physical deletion. Okay, and the goal, or what data structures really like to do now, is they, at some point, like to unlink or physically remove all the logical removed nodes so that they do not pollute the structure. How do they do that? Well, they start at some unmarked node. How we get there is irrelevant for this talk. And then they traverse this marked segment and they traverse the segment to get to the first unmarked node. Let's call this node right. And then they try to, and then they remove all the marked nodes between the left pointers. So in this case, from minus infinity to the right node D. And so they unlink all these nodes in one shot, and there might be an arbitrary number of nodes in this segment, as indicated here by the dots between B and C. And for verification, this poses a challenge because we now need to show that the sets are equivalent, right? So the set on the top, it just contains the one value D because everything else is marked. And now in the updated set, we need to show that it is still sorted and that it still contains the same logical contents, in this case D. So how do we do that? The classical reasoning would go something like that during the traversal, you would perform something that I call like shape discovery. You would need to come up in terms of separation logic with a recursive predicate that encodes the fact that this is a marked segment and does not contain any logical contents. And then once you do the update, you would need to show that removing anything that is denoted by this recursive predicate can, so to speak, safely be removed, maintaining sortedness and the logical contents. And this usually involves some sort of inductive reasoning over the recursive separation logic predicate. And the problem with that is that that's really hard to automate. So both steps are hard to automate. So it's unclear how to discover this shape, come up with a recursive predicate in a general setting, and it's not clear how to do this induction in an automated fashion. So what we suggest to do is something we call ghost update chunks. So we suggest to compose this complex update that we are doing into smaller ones. So we start by just saying, okay, you know what? We know how to show that we can unlink A. So we first show, okay, you can unlink A, and this update would maintain the sortedness and the logical contents of the set. And then we go on and say, you could also unlink B, provided you have already unlinked A. As you can see in the second update chunk, we are now starting in a set where B is the immediate successor of -infinity. So we assume that A has already been unlinked, and we show that we can unlink the single node B. And this single node unlinking is easier to handle, and we know how to do that automatically. And then we go on through the entire list, and we finally show that we can also unlink the single node C. And as you can see, these update chunks can now be chained together. So the post condition of the first update chunk entails the precondition of the second one, so we can use the sequential rule of the Hall calculus and chain them together to obtain the overall complex update that unlinks A, B, and C, and everything between B and C. Okay, so to convince you that this is a useful technique and works in a proof, I would like to make this argument of our ghost update chunks a bit more formal and give you a proof sketch of the above removal. Oh yeah, one important thing that I forgot to say is that all of that can be done during the traversal in lockstep with the program. And this is really helpful for automation to when we automatically generate the proof, as we will see in the proof sketch. For the proof sketch, you don't need to be afraid of separation logic. I won't show you any separation logic formulae. I will draw pictures that if we were to do the formal proof, we had to state them in SL terms. Okay, so the first step of the traversal looks something like that. We start in a state, in the current state where we have already acquired the left pointer where we started our traversal, and we have its immediate successor right. And now the traversal finds that this right node is marked and continues to the traversal, so it reads out the successor node. And in this state, we can immediately perform or come up with our first update chunk. So we can show that in this state, we could unlink right. And this is really just hypothetical. We show that we, in this state, could unlink right and make the next node the immediate successor of left. And now we apply a neat trick that we will see in a minute why it is so cool. We discharge part of the premise of this update chunk. So we know that the right node is marked, which in concurrent data structures usually means that this node becomes immutable. It won't be changed anymore. So going forward, we will know that right will always point to next, so we can discharge this part of the premise of this update chunk. Why can we do this? Because our update chunks are basically Hoare triples with a twist. And the twist is that we do not need them to be valid in general. We only need them to be valid under the current state, under what is denoted by this now box. And because the now box tells us that right points to next, we know that we can, so to speak, dispose of that in the update chunk. Now, going forward in the proof, we just continue our traversal. So we move right to the right, which in this annotation means we just do a renaming. So everything that was next before becomes now right. And I took the liberty to simplify the annotation here so that we do not spill. So I removed this node A in the now state just to make the presentation a bit more lightweight. Okay, so that's the first step of our traversal, and then we go on to the second step. Okay, so we start with the result of the first iteration, and again, we find that the right node is marked, so we continue our traversal and read out its successor. The update chunk does not change because we haven't done any work there. We still only know that we can remove anything between left and right. And what we now want to do is we want to show that we can additionally remove right. So how do we do that? So first, we introduce a new update chunk. And it's the same one that we had in the first iteration. We say, you know, if we already removed everything between left and right, we can also remove right, because that's a simple update, right? Left, right, and next are immediate successors, and right is marked, so we can remove this node without without changing the sortedness and the logical contents. And the next step we want to do is we would like to merge these two update chunks. But right now we cannot do this because the post condition of the first update chunk does not know anything about the next field that the precondition of the second update chunks needs. So we apply our favorite rule, the frame rule, and get or add this additional knowledge that there is this next, this node next, and that it is the successor of write. And now we can merge, because now the post condition of the first chunk implies or entails the precondition of the second chunk. So we get the overall update, chunk that says we can remove everything between left and next. And again, we play our trick of discharging part of the invariant, the precondition, sorry, because we again, as before, know that the right node is marked and it is pointing to next, so we can get rid of that. And again, going forward in the traversal or moving our right pointer just means that we need to rename what was next before to right. And now we are in a good spot because we see that the annotations at the beginning of our second step of the traversal and at the end of the second traversal are the same. So they are syntactically the same, but the second update chunk removes one more node. And this means that this annotation can be used as a loop invariant and really captures our intuition of, going through an potentially unbounded sequence of marked nodes and removing them all. And we have the right annotation to capture that in a precise manner. Okay, so in the paper, we formalize this concept of ghost update chunks in terms of abstract separation logic. And more importantly, we give these usage patterns that I just used in the proof sketch, namely the introduction of update chunks, the merge, the frame rule, and the discharge, and we show them all sound. On top of that, we also provide an implementation, so a proof generator or a proof generation tool that uses this technique to generate proofs for complex updates using this technique. Okay, that's it for complex updates. So we've done that. So we just need to address the second challenge. And the second challenge here is linearizability. And I'd like to motivate, again, by an example, what the problem or what the challenge with linearizability is. So let's consider, again, a sorted set in this example containing the values 5 and 7. And we want to check whether 7 is contained in that set. How do concurrent data structures usually do that? Well, they again perform some sort of a traversal to a node. Let's call this node X. And once they arrive at that node, they like to sort of inspect this node. So they like to check whether the value they are looking for, in this case 7, is contained in this node. But because it's a concurrent data structure, they are subject to interference. So there might be some interference that just in the meantime unlinks this, or so remove and unlinks this node 7 from the set. So in this state, 7 is no longer contained in the set, but data structures tend to be a bit more relaxed and still go forward with node inspection. So they still look at the node, find the value 7 there, and say, you know what, this is good, and they will say, in this state, 7 is contained in the set. So that sounds a bit weird, but we are fine with that because that is what we consider linearizability, because 7 has been in the set at some point, right? At the moment we reached node 7 in the traversal, we know that 7 is contained in the set, but the algorithm only learns that later. So for us, for verification, to do verification, the proof goal is to show that this, at some point during this algorithm, 7 was really contained in the set. So that is our proof goal. And in classical reasoning, This would be done with prophecy variables. So you would do a prophecy about the outcome of this inspection, which is kind of a case split. And then when the inspection happens, you would just reconcile this outcome. The problem with that is that it's hard to automate because there are so many possibilities of values to split on. So there are so many case splits that we can do, and where to do them is also unclear. So we suggest another approach that we consider past reasoning. So we suggest that during the traversal, you just record the past state, and once you do the inspection, you propagate that outcome into the past state. So this provides you with the illusion that at some point, so that you have done the traversal, and in the moment you do the traversal, you also do the inspection. To be a bit more precise, I again want to give you a brief proof sketch of how that would look like. So we start in a state, or we start this proof sketch in a state where we reach the node X that we are traversing to while it is still linked. And now we just record this information in a past state. So this just says that this setup was true at some point in the time. Maybe not at the very moment, but some point in the past. Now, if we get some interference, the interference will still unlink X from the structure, but it will not change our past information. Okay, so the interference can change the current state, but it cannot change the past. Now, if we do our inspection, which is just a fancy way of saying that we check that X really contains our search keys, say K, we find that the value B in X is equal to K. And we can now propagate this value into our past state. And we can do this because the values A and B that I put here in the now and in the past state are not just there by coincidence. We track the relation that the value B that is stored in X, whatever it is the same in the current state and in the past state. So we retrospectively learn that in the past, X contained value K, meaning that there was a point in time where the set contained value K. So returning yes is in fact a linearizable, so correct answer. Again, we formalized this technique in the context of abstract separation logic and showed the soundness of this lightweight instance of hindsight reasoning that is this propagation from the current state into the past state, and we provided an implementation of this in a tool. So to recap, we presented a concurrent program logic geared towards verifying concurrent data structures, and our contributions are these update chunks to handle complex unbounded updates through simple updates, and these past states so that we have a lightweight way of hindsight reasoning to prove linearizability. And we have implemented this tool that can verify challenging examples. For example, the Harris set that no tool could verify automatically before. And with that, I'd like to thank you for your attention.
Yeah. Interesting work. Thanks for that. So just a question about the scalability, because it sounds like you'll probably have to record lots and lots of past states.
Yeah, we record a lot of past states, but we kind of try to record individual nodes. So if I go back here, we would try to record precise information only about a single node and not about the entire sequence that you might see in a proof. So we would record that, okay, there is a bunch of nodes, so it's a set data structure, but precise information say about X, but not about the other node A that is in the context.
Okay, but every time you get some kind of interference, you'll have to record another past state, is that right?
Yes.
Yeah.
Yeah.
Okay.
But also we can then see whether some of them are less expressive or contain less knowledge, so that we can prune a lot of those that are irrelevant. But still, we get a lot of past states. Yeah, that's true.
Okay. So maybe just a follow-up question. These benchmarks, how big are they?
So Harris set is, oh man, I say between 50 and 100 lines is Harris set, but it's a very challenging benchmark that no tool could verify automatically before, and I think even paper proofs are, I'm not sure if there is a mechanized version of that proof.
In terms of parallelism, are there any bounds in the parallelism?
Sorry?
Are there any bounds in the
Oh, no, this is thread modular in the sense that these proofs work for an arbitrary number of threads. No, I'm good. Yeah.
Okay, so we have time. We have time for more questions. We finished a little bit early, so the questions, please. Yeah.
Very nice work. I was wondering, when you were talking about the chunks, right? I was wondering how they help you in guiding the automation. Like you can imagine, you know, that you discovered that you wanted to have a chunk of some form maybe later in the proof. How do you handle which chunks to generate at a specific point?
So in the tool, this is like governed by the updates that are performed. Basically, we look at the compare and swaps that are in the program because they give us a good idea of what updates are going to be performed. And based on that, we just say, okay, let's assume this will be a complex update, and we try to, you know, just compute all possible chunks that lead to this update. So again, we are computing a lot, but it's much less than doing, you know, it's easier to do than like shape discovery and reasoning about recursive predicates.
More questions, discussions? Yes, over there.
Thanks for the interesting talk. I'm wondering about your definition of automatic, and here at the end, the first two verified challenging examples like Harris set. Because if you use an automated tool like Verifast or Viper, you might not have like the right automation for the problem, but you can always add annotations here and there, direct a bit more the proof using some directives. So do you mean that Harris set, an example like this, is impossible to verify in this other verifier? Or it would be possible, but you need to add a lot of annotations and it's not automated anymore?
So yeah, first thing, when I say automation, there is 0 annotations in the programs. So we don't need to add anything. It's just you give it the program code and it generates the proof for you. So there is 0 overhead in writing annotations. With respect to like semi-automation in Viper, I'm not an expert on Viper, but I could imagine that you would need to like do the key reasoning of linearizability in these update chunks. That you would need to say, oh, you know, create an update chunk here, piece it together there, and you know, use it in that position. And for linearizability, I guess you would need to say where to record the past state. And I'm not sure about Viper, but I guess you would also need to give some loop invariance to do that. So I would be afraid that there is a large overhead of annotations to do, which in our case, we are free of that entirely.
Okay, please let us thank the speaker. Thanks so much.